Okay.
Sure, mine in my backpack. It's all folded and stuff.
Happy Friday. A little chilly outside. Let's see here. Wednesday, we continue talking about material properties, right? This amazing test that we conduct on materials, right? The stress strain response test where we put a specimen into a machine and we pull on it, we measure the displacement, we measure the force. Knowing some of the cross-section, the geometry of our specimen, we can figure out what the strain is, what the stress is, right? And we get this curve. And this curve allows us to come up with a whole slew of things that we can use as designers. Some of the biggest things we ended on Wednesday with was this relationship, right? We get this Hooke's law, strain is stress over our modulus of elasticity from our stress strain response, right? We know what the definition of strain is, right? Change in length over the original length. And we know stress is just force over a cross-sectional area. Using all of these and plugging them into each other, we can finally get this force deformation relationship, which comes from, right, the definition of stress, F over A. We get change in length over the original length, that's our strain. And then finally this material property, which is our modulus of elasticity, E, which is essentially just the stiffness of our material, just like a spring, okay? So we can relate deformation to loading, geometry, and material properties, which is our modulus of elasticity, okay? So that was a big thing to take away. And we're gonna use that deformation is FL over AE when we get into axial systems here later today, hopefully. Before we get there though, in chapter 4 of the text, it talks about this idea of design concepts, right? So as I've mentioned already in class, this class is bridging the gap between internal forces, right? Your free body diagrams and statics, right? Adding to it materials, right? How do those materials behave under a certain load? And then taking it one last step, right, that actually gets us to reality, which is how do we then use this information to our advantage so that we can design something that's not going to break or fall down or kill somebody, right? So in chapter 4, we talk about this. Well, the big picture of all of it, if you could boil it down to something, I would say that the big picture is the allowable system capacity right, has to always be greater than or equal to the system load. Okay. You always got to make sure that that chair you're sitting on has more capacity than you're imposing on it by sitting on it, right? This has to happen for everything, right? When it gets cold outside, you got to make sure that the HVAC system for the university is able to handle, right, the demands upon it. If not, then we get broken pipes and uncomfortable patrons like yourselves, right? And so we always got to make sure that the allowable system capacity is greater than the system load. When we design things, we incorporate a lot of different components, right? I think the common one, obviously, is we want to make sure that what we're designing has adequate function, right? If it's a chair, better well serve its purpose very well, right? If it's a desk, if it's a medical instrument, right? A bicycle chain, things like that. It's got to serve its function. Money drives everything, okay? So obviously, initial cost becomes an issue. Right? Want to make sure that we don't go broke trying to design this or build this component, right? Any other ideas of things that you would consider when designing something? We've got function, we've got initial cost. looks, aesthetics. Anything else? Yeah.
Liability?
Liability, that'd work.
Maintenance costs.
Yeah, and then with liability, I'd say, right, safety. I'd call this what we would call life cycle cost. Sustainability, right? Environmental impact. For you CETs out there, you'll learn about, if you haven't already, LEED certification with the Green Building Council. Right? All new buildings on campus have to meet one of the tiered approaches for essentially sustainable design. And they essentially go through and they limit, right, how far away from the job site you can procure materials. And you get dinged if you are transporting something from, say, New York to build something in Bozeman, right? If you're gonna get your cement powder, right, you could get it from, say, Wholesome out in Logan, right, out in Trident, okay? You wouldn't wanna get it from, I don't know, Texas or something like that, okay? Also with respect to HVAC systems and cleanliness and recycling of building materials as you're constructing things, sustainability has become a very big component, okay? So we think about a lot of things when we're designing a component, right? Not just what we're talking about in our class. In this class, though, we do look at kind of three components. There's the big one, right, with function. And as it relates to materials, right, we want to make sure we have adequate strength. We look at this via stresses, right? Sigma or tau, right? Shear stress, normal stress. We also have stiffness. Which drive deformations. Right? I guess add another design component, I'll say serviceability. Oh. Serviceability, right? I think I've talked to you a lot about vibrations is a really big one for civil engineers. Okay. Things could be strong enough, but then it might not be stiff enough, right? And be able to serve its purpose because it's vibrating all the time and people can't actually work in the area in which they're supposed to because the floor vibrates, right? Last one. Might be strong, it might be stiff, but it might inherently be unstable, so we need to look at stability. This has to do with buckling. Columns is a big one we'll look at. We'll determine this idea of what's the buckling load of a column. So we're really trying to just size a particular part based on given loads, material properties, and maximum deflection requirements. Loads, material properties, and maximum deflection requirements, okay? I'm biased because I'm a civil, and so I know a lot about buildings, right? So when you design rafters and a roof system, okay? Right, in this one we've got this acoustical ceiling tile inlay, right? All of these wrapped tan things are likely beams, okay, spanning over here, right? So if these beams are wrapped in, say, some sort of gypsum board or stucco, right? The code gives us different deflection tolerances for what those elements can deflect between wall to wall in order to not degrade the actual finishes on that beam, okay? So they give that in a span ratio, right? So it might be L over 360. Okay? If you're designing, like if you go to a lot of the brick buildings on campus, right? A lot of the openings have what we'd call lintels, right? That support the brick. Those lintels have to be L over 600. So like really, really tight tolerances, right? So that's in order to keep the brick from cracking, okay? To give some perspective of this, like an L over 100 is something that you can actually physically see. Right? So L over 600 is very, very small. So we size our particular parts in this class based on given loads, material properties, maximum displacements or deflections. Right? These loads are determined in other classes. Right? And obviously there's inherent variability. In their development. Right? Engineering is just a big educated guess, right? That's all we're doing. Okay? It's got to be defendable. So we cannot perfectly analyze loads, right? So we have material codes or governing codes, like the American Society of Civil Engineers, American Society of Mechanical Engineers, right? ASME, ASCE, right? They'll come up with code requirements for the design of boilers, right? So if you're going to design a boiler and you have things under pressure, they'll give you pressure requirements with which you would then design your boiler for, right? The pressure vessel of the boiler. ASCE has design requirements for this building that we're sitting in, right? Where do you get your snow loads, right? Where do you get your snow loads if you're sitting in Colorado? Where do you get your snow loads if you're sitting here in Bozeman, Montana, right? What are your wind loads? What are your seismic loads, rain loads, flood loads? It goes on and on and on, okay? A lot of research has been done to try and pinpoint what that is, what those loads are, but inherently there's variability in it, right? And things change over time too, okay? Right, we had 2 gyms collapse, and the snow loads that those buildings were designed to are not the snow loads that new buildings were designed to, okay? Those were designed for like 30 pounds per square foot, which is currently the state minimum. But if you're in the city limits of Bozeman, you got to design for 40, okay? So inherently there's variability in loads. Well, there's also variables that we can't control altogether, right? Can't control how things age. Right? One of you said maintenance cost, right, is a design component. Right? Well, we don't know how good one owner is going to be at maintaining their structure or their component, right, or element. Right? One mountain bike rider might be super meticulous at oiling and cleaning their chain, right, adjusting their derailleur and stuff, and then another owner could just take their bike and let it sit outside. Right? So how things age, we cannot control very well. Quality of materials. We like to think that we can specify this very well, but in reality, there's still inherent variability in the quality materials we get, okay? There's ASTM testing that goes into specifying different materials, like A36 steel, okay? Has a yield stress of 36 KSI. There's also a lot of different requirements. If you go to the ASTM A36, it'll give you different chemical composition for that steel, testing that needs to be done on certain lots of the steel, right? They're not going to test every little piece of manufactured steel, but they're going to test a certain amount, right? A certain portion of the steel that gets produced at a given time to try and verify it. But there could be impurities or things that are messed up within one plate, right, that goes out. So the quality materials, there's variability there. Also, alterations over time. Right. University is fairly consistent with this, right? If you're going to build a academic building, typically, for the most part, it'll stay academic, right? Classrooms, offices. Sometimes you maybe take a classroom and make it into a lab space, right? The 6th floor of Cobley Hall is like all lasers, NASA stuff, right? 3rd floor too, okay? Those labs, that building wasn't likely designed or had the expectation that they'd have these very, very tight tolerance type lab spaces, okay? So things change over time, right? Buildings downtown, for instance, it might go from a office building to a gym, right? A fitness place. That obviously changes things for the building and its purpose. So in order to incorporate and try and cover all of this, and honestly, to me, it's just a way that people sleep at night, is we add factors of safety, right? We say, okay, this is what we think it's going to be. We have some inherent uncertainty on where our loads are coming from, the materials that get built, how it's going to be used over time, how it's going to age and be maintained, right? So for me to sleep at night, we're going to impose factors of safety. A lot of times denoted as FS, okay? And as I mentioned before, right, one of the considerations for design of any component is its initial cost, life cycle cost, right? Money drives a lot, okay? Economy. It's got to make sense from a fiscal standpoint in order for it to get built. And so a lot of effort is spent understanding the loads and uncertainty, because as our uncertainty goes up, our factor of safety goes up, right? For a building, factors of safety depends on the component within the building, but you might range from 1.7 to 5 as your factor of safety, depending on what you're designing, right? If it's a very critical component, critical to the, say, earthquake stability of a building, right? And it came down to one connection in one portion of the building. And if that connection failed, right, the building was going to come down. Then that connection, right, the code, we as engineers and designers, impose upon that connection a higher factor of safety because we do not want it to break, right? It's like the fuse in the entire system. Whereas if we were going to look at, say, one of the beams above our heads here, right, very repetitive sort of system, lots of them there, the potential to have redundancy, right? One sags a little bit or fails a little bit. Some of the other ones might be able to pick up the load. That's where we're kind of down in the like 1.7 range, 1.67, okay? Obviously airplanes, right? They need to get off the ground. They can't be too heavy. Cost goes way up so that they can reduce the uncertainty. Which they can reduce the uncertainty, they can reduce the factor of safety, right? A friend that went to school with me works at Boeing, okay? one of the crazy design applications that they impose, or design requirements they impose upon new aircraft, is they call it the 3-foot sphere of death. Okay? Anybody heard of the 3-foot sphere of death? 3-foot sphere of death, you could take in an aircraft and take like a sphere that was 3 foot in diameter and place it anywhere inside the fuselage and delete everything inside of it, and the plane should still be able to land. Okay? So I mean, obviously you're gonna have redundant systems, right? Because you might put that sphere of death somewhere that cuts off your ability to run the elevator or the rudder, right? And so, things might be run on either side of the fuselage or something like that. I heard that and that was blown away. I was blown away, right? Other crazy thing to get on a tangent, the turbines, jet turbine engines, right? The fans in them for your MUTs. I had no idea that it gets so hot inside a jet turbine engine that they end up having to, in the blades of the turbine, they have a bunch of tiny little holes that they pump air through so that there's a small film of air over each one of the fins that cools the fins, because if it didn't, it would melt. So it'd essentially just eat itself to pieces. Yeah, I learned that, and then I went on like a overseas trip on an airplane for like 12 hours, and I about freaked out. Right? Because I was on an aircraft with only 2 engines, not a lot of redundancy, right? It's like, shit. Really cool stuff though, right? So obviously airplanes, they put in a lot of effort to reduce the uncertainty, do a lot of testing, a lot of modeling, so they can reduce the factor of safety. So obviously with the increased factor of safety, your demands go up, you need more material, right? Things need to be stronger, need to be heavier. So as part of this factor of safety, we have this idea of working stress and max stress. Working stress is what we would call our allowable stress. And that's our max stress divided by our factor of safety. Okay? So we're going to say that our material can go to a certain point. We're going to say, screw that. I don't feel comfortable with that, right? Based on a lot of different things. So I'm going to reduce that by what makes me feel good, which is a factor of safety, a margin of error, so that I can get an actual allowable stress, and that's what we're going to design our components to, this allowable stress. Right? Anybody have seen this idea of WLL, or working load limit? Is what WLL stands for. Right? If you went to Ace and you were buying a small hook that you would screw into the wall, or a clevis, or a carabiner, for instance, right? On the side of it, it might say WLL 3,500 pounds, right? WLL 2,000 pounds. That is the working load limit. And that's saying, okay, based on the allowable stress, that's how much load you can put on. So there's a factor of safety built into that. So if you put that carabiner, right, or hook, or clevis, snatch block or something into a system, right, you're going to be confident that you can get that load out of it, right? You can impose that load on it. Well, max stress, right? We need to have this stress which we classify our material as failure, right? So we call our max stress our failure stress. And our failure stress can be different. Right? It's not just the same value for every material. If we go back and we look at our stress strain diagram, right? We have sigma, we have epsilon, right? Stress and strain. And we had a couple different types of materials. One might do something like this. One might do something like this. Right, this material here would be a lot more ductile than this material. Okay? It undergoes a lot of permanent deformation. This material, it just keels over. Right? There might be a little bit of a yield right? We have this area we call where we start leveling off. Right? We'd also have in each of our materials an ultimate stress, right? Right? So we'd have a yield stress and an ultimate stress. The green and the red there. Well, we as designers get to choose what constitutes our material to fail. Right? What is the failure stress for our material? Sometimes it can be called out as the ultimate stress, right? Are you going to wait until this material actually fractures? Right? It's going to fail. If you go to the failure or the ultimate stress, it will fail. Or is your failure criteria, you don't want it to yield, right? You don't want to get to the point where it's going to hit this plateau, right? It's going to turn into taffy, and now we're going to get a lot of deformation. And so you can choose, and depending on the component and what it's used for, they might choose the ultimate stress over the yield stress. I would say the yield stress is the more common. Failure stress. As if we ever did reach that failure stress, which would be the yield stress, right? We're going to have a lot of deformation. And it might be beneficial to pick that as the failure stress also, because that doesn't necessarily mean it's going to fail at that level either, right? It's going to have a lot of deformation, but there is still some residual capacity between these two, leading to maybe a little bit more factors of safety and make us sleep a little bit sounder, right? So if we look at factor safety now, right, it's the max stress over the working stress. Right, this being our allowable stress. So if we look at it in terms of, right, we have stress is force over area, and we have our shear stress as our shear force over the area, right? So if we relate our factor of safety with respect to stresses, we could say the factor of safety is our failure stress divided by our allowable stress. Right, or actual stress. Right? We might, as designers, impose a factor of safety, right? Or if you were going and analyzing a component, right, and you knew what its failure stress was, and you know the demands on that element, you could figure out what the actual factor of safety is for that component, right? If you had a situation in which the component was actually being used in, you could go back and double check, right? If you were in a building or you had this component that was originally used for something, it was designed for a factor of safety of say 5, then the use on that component changed and you wanted to go back and check what the factor of safety was, you would essentially take your failure stress divided by the actual stress for that system, and you could figure out what the actual factor of safety was. Similarly, right, you could do the same for shear. And get the same thing, okay? Any questions on that before we go to example? Yeah?
How does it give you the same thing? Like, would it both give us the same number?
They are both going to give you your factor of safety. So if you started with a fresh design, right, and you knew what the failure stress was and you knew the allowable stress that you were going to impose on the design, right? You could then calculate your factor safety. If you were analyzing an existing component that you didn't know what the factor safety was, then you would calculate what your failure stress was, right? Based on whether you selected yield or ultimate. And then you would figure out what your actual stress is by calculating the force on the system over the area of the system. You divide the two and you could say, okay, right, say you had a steel chain, okay, and it was holding a load on it, and you initially designed the steel chain for the load that was imposed on it for a factor safety of 5. And then someone came in and said, all right, I'm going to add 300 more pounds to that load. What is the factor of safety now? Then that's when you would put in, okay, what's the actual stress on that chain in the denominator? You knew what the failure stress of the chain is. You would calculate, okay, instead of being a factor safety of 5 now when it was originally designed, you're sitting, if you add 300 pounds to that load, you're sitting at a factor safety of, say, 3.2. And then you could evaluate as an engineer, okay, based on the uncertainties here, do I feel comfortable with that being there with a factor safety of 3.2? Does that make sense? Okay. Let's do an example. Okay. So we've got a splice plate, right? Might be in a brace frame in a building or something like that, okay? Some sort of tension member. We've got this axial load P, axial load of 200,000 pounds is sitting on this splice plate. Might be the truss component in a bridge or something like that, okay? They tell us that the ultimate stress of our bolts, tau ultimate, is 125 KSI. So this is our ultimate shear stress allowed in the bolts. They tell us that based on this component, the uncertainty, what it's used for, they would like us to impose a factor of safety of 1.6 on this design. And they want to know what's the minimum bolt diameter, okay? They also say, all right, we've made this evaluation that we're going to say that the failure stress is actually the ultimate stress for our bolts. So tau ultimate equals our failure stress, and we're going to say that's 125 KSI, right?
So they let this thing deform a bunch before?
Yes, potentially. Yep. It could shear a little bit. These bolts could plastically deform or permanently deform, right? They will, because they're going to be greater than the yield stress. But they're saying that we're not going to consider this completely failed until you hit the failure stress, which is 125 KSI. Okay. Well, to start this out, I'm going to draw a free body diagram. All right, we've got, if we were to cut it and take the right-hand side of our plate system out, right? Our externally applied loads is P. We're going to have 4 bolts, but if we look at this in section, we're only going to see 2 of them, right? These bolts are going to extend between our plates like that. As we derived earlier, right, when we talked about shear stress, we know that each one of these bolts is going to have some sort of shear force on it, right? And in order to maintain equilibrium, right, adding up all of the shear forces in each of our bolts needs to add up to P, right? Well, if you look here, we've got 4 bolts. Each of those bolts has 2 planes over which our force travels, right? Because overall, if we looked overall, we're going to have a force in our upper plate, right? Cheek plate on the top and the cheek plate on the bottom, right? The splice plates. Those forces, because some of the forces have to equal P. So we're going to have half the force in the top plate and half the force in the bottom plate. We have 4 bolts, right? Each bolt is in double shear. Right, we have 2 shear planes per bolt, is what that means. So we have 4 bolts total. We have 2 shear planes per bolt. Right, 4 bolts with 2 planes per bolt. So we have a total of 8 shear planes. Right? Well, we have our definition of shear stress. What's the equation for shear stress? Right, tau equals, remember, safe space. Something? Somebody say something? Force over the area, which in our case for shear stress, what's the force? V, right? It's a shear force. Same thing. V over A, right? Well, out of this, they are telling us they want the minimum bolt diameter, right? They want A. We can figure out V, right? Based on the shear planes. And tau is also given, right? That's our failure stress with our factors of safety imposed upon it. Right, so if we rearrange this with our known values and unknown values, right? So we have V over tau. Well, our shear force has to do with our imposed, right? Imposed load P. And that P has to go through all of our shear planes. We decided that we have double shear, right? Each of these bolts has 2 shear planes. Because each of these bolts has 2 shear planes and we have 4 bolts, we have 8 shear planes. Right? So the load imposed on each one of our bolts, right? Each of our bolts shear planes would be the total load divided by the number of shear planes, right? V equals P over 8, right? That would be 200 divided by 8. That equals 25 kips. We have tau. If we're figuring out our minimum bolt diameter, right? We want the diameter that will meet our design requirements. Our design requirements are that our ultimate stress is 125, right? That's our failure stress. But we were told that we wanted a factor of safety of 1.6. Right? Well, we know that our factor of safety is our failure stress over our allowable stress. Well, we're going to want to figure out our allowable stress, right? We were given these two. We know when the bolt is considered to be failed. We know the amount of factor of safety that we want to impose upon it to feel good at night, right? And so we're going to make sure that our component that we actually design doesn't exceed this allowable stress so that there's a factor of safety there, right? So if we take our tau failure and we divide it by our factor of safety, we get our allowable shear stress. And that's what we're going to want to put in there, right? That's what we're going to allow the component to reach. Anything beyond that and it fails. It doesn't fail in the real world, but it fails based on imposing a 1.6 factor of safety, right? So let's take this and we're going to say, this equals 125 KSI divided by 1.6. That's 78 KSI. Now we know that our minimum area, right? Anything larger than this, right? Anything larger than this, we got a larger diameter. If we have a larger diameter, our shear stress is going to go down, right? We also want to minimize materials when we're designing things, right? Materials cost money. Fabrication costs money. So this is going to be a minimum area, and we know that that minimum area is now our V over tau. In our case, we decided it's 25 kips over 78 KSI. Well, if you notice, the units work out in our favor also, right? Kips over KSI gives us square inches. So our minimum area is 0.32 square inches. Well, we're not quite there yet, right? This is a minimum area, and they asked us for the minimum diameter. Right? Diameter of a circle with respect to the area of a circle with respect to diameter is pi over 4d squared, or pi r squared. You get that, set that equal to 3.2 square inches, solve for d, and you get a minimum diameter equal to 0.64 inches. A little over 5/8 of an inch. So in this condition, we ran through and we applied that factor of safety to the stress, right? We took a failure stress divided by our imposed factor of safety. Yeah.
Could you talk about the double shear versus like single shear? Like parts of the bolts? I noticed that was in the homework.
Yeah. So double shear, all that means is that every bolt has two shear planes. So what that means is that every one of these bolts, right, we're transferring, because we have a plate on either side, that force that is running through our system essentially has to go through two planes to transfer out of the system, right? So we've got the load over 2 on the top and the load over 2 on the bottom. Because of symmetry, we did a little derivation earlier in the class. Right? These forces are equal. We just took an overall free body diagram, take this out of here, right? We cut it at the we cut this system right here, right? Deleted everything here. These plates are not continuous, right? We're actually taking the load out of this plate. We're going to impose it into our splice plates. Come across, it's going to splice it back, put it back into the plate again, right? So if we cut it right in the center, the only thing we have continuous across this cut is the splice plate on the top and the splice plate on the bottom, right? And then we have our main plate that continues on to the right. So if we drew a free body diagram, which we did here, that's what this is. We know that that interior plate, it ends right here, we know that, right? That interior plate has a big force P on it. And we know that because of equilibrium, the forces going that way have to equal the forces going that way. Otherwise this plate's going to be moving, right? So the forces off to the left have to equal P. Because of symmetry, right? You can sum the moments about any arbitrary point here. And you're going to say, okay, we got P over 2 going this way, we got to have P over 2 going that way, right? And this one's twisting this way, this one's twisting that way. So these forces are equal. And if they're equal, it means that they got to be half of P, right? P over 2. Now that we know that we have these forces in these splice plates, that force in the splice plate has to make its way through these bolts, right, and into the center plate. And it makes its way through the bolts by trying to shear each of these bolts off, right? So we've got essentially a shear force there, a shear force there, right? This splice plate on the top and bottom is pulling on those bolts, okay? And it's pulling on those bolts with a total load of P over 2, right? So if you took P over 2, right, and you divide it by 4, because each of these bolts has a quarter of P over 2, right? Well, there's the same thing going on the bottom. So you've got 4 bolt surfaces, right? 4 shear surfaces on the top, 4 shear surfaces on the bottom. That's where you get your 8 from. So for every bolt in a double shear connection, you've got 2 shear planes. That's what double shear means. Does that somewhat answer your question?
Yeah, so if you said single shear, it would just be like 2 plates instead of 3.
Yes, correct. Yep, if it was single shear, you would then essentially delete this bottom plate, and that force, right, P, would be going through just one shear plane in each of these bolts. The bolt's only trying to shear off at one location.
So you just have straight up P.
Yep, so P over 2, this would just be P, right? And you would divide P by 4 instead of by 8.
So the only way you have like 3 shear planes if you had it in like 3 different ways? Or is that?
You could definitely do that. You would have to add additional splice plates, which would, I mean, a 3 connection would look something like, right? And you ran a bolt through this entire thing. Oh, 3 would be tough. That's 4, right? Right, you've got this, 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 which means you have a shear plane, right? Here, 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 and here, right? Trying to think of how you would get. Oh, you could delete the bottom one, right?
So if you take the bottom
Yeah.
piece off, would it make it green?
Yep. So we could take this off, and now we're down to 3. Right? All right. Any other questions? No? Okay. We'll stop. Which means we'll start axial deformation on Monday. Don't forget, there's a quiz, right? Quiz is out on D2L. It's due by the end of the day today.
It's due at the same time we're working.
No, it's due actually by midnight.
Oh.
Yeah.